All right, Chem 11 students. Our next topic is carbon-hydrogen analysis, and this is the second part of the decomposition reactions being used for the purposes of formula determination. All right, so this lecture, this is not the first slide. This is a continuation of the previous lecture where we did hydrated salts and we did oxides and their decomposition and us being able to determine the formula of the substance based on its components that it broke down into when it underwent a decomposition reaction. So today we're doing carbon-hydrogen analysis. What you're going to need today to be able to do the problems that are in this is a periodic table-o-matic 3000. I've got mine here because of course we use the average atomic mass as the molar mass for each of the elements and compounds. So we'll need that. And we'll need the calculator-o-matic 3000 solar powered addition for this guy. So even when the lights go out because of an electrical impulse, this guy can still do chemistry. Anyway, I've got that off to the side as well. So let's go through. I'm going to pull my chair in. Sorry for the noise. So let's go through a carbon-hydrogen analysis, what it means, all right? So to determine the formula of a compound that contains carbon and hydrogen, chemists use what's called a combustion analysis, all right? So we've seen these before, right? These are hydrocarbons. Anything that is made of simply carbon and hydrogen, and that's it, no other elements, that's a hydrocarbon. And the values that go there, it can be anything. There's so many different hydrocarbons out there, right? We've talked about a few in class, right? For example, if you're down in the shop and you're welding, you're using ethine. So ethine is the gas that's used in the welding tanks along with oxygen. There's two tanks. One is ethine, the other one is oxygen for the combustion, right? You need those two things, the fuel and the oxygen. Another one in your barbecue tank is propane. Propane is C3H8. And a lighter you have butane, C4H10. Gasoline in your automobile is C8H18. This is octane. All right, so you can see the same two elements are involved, but the ratios are a little bit different, right? The numbers that we're putting in these two positions. So this is what we're going to be able to find today, those two numbers right there, by doing a combustion analysis where we're able to figure out the parts of hydrogen and carbon that go in there. All right? So, how do we do this? Well, what we do is we take a known mass of the unknown hydrocarbon, right? So put X and Y here. We can do that as well. So we take a known mass of this hydrocarbon and we put it in a carbon-hydrogen analyzer. And we burn it at a very, very high temperature. We pump oxygen into this thing so it's complete combustion, very, very efficient combustion. And you can see here, here's basically what we do. So we take our hydrocarbon fuel, we pump in oxygen gas, and of course the two products that we always get from a complete combustion are water and carbon dioxide. All right, so this is what we do. What happens is we can get the mass of the water that is produced, and we can collect and get the mass of the carbon dioxide that is produced. All right, now, how does this relate back to that? Well, if I look, the only carbon going in is in my hydrocarbon. The only carbon coming out is right here. So I'm going to use the carbon amount, and amount is moles, in my carbon dioxide to figure out the amount of carbon in the formula. For hydrogen, the only hydrogen going in is right here. There's none here, and there's none here. So this is the only hydrogen going in, and the only hydrogen coming out is right here. So I will use the amount of hydrogen in my water to figure out the amount of hydrogen in my hydrocarbon fuel. Just like I'll use the amount of carbon and carbon dioxide to figure out the amount of carbon in my hydrocarbon fuel. The only way carbon goes in is here. The only way it comes out is right here. Hydrogen only goes in here, it only comes out here. So we use water to find hydrogen, carbon dioxide to find carbon. And that's what that last point is saying. Carbon dioxide is the only source of carbon, hydrogen or water is the only source of hydrogen in the products. All right? Here's what it would look like. So this is our furnace here. Our sample goes inside of here. You can see it's on fire. We pump oxygen through. It's a complete combustion. Now there are a couple of chambers after this. One of them contains a substance that absorbs all the water. So if I weigh this chamber before the combustion and then weigh it again after the combustion, that difference in the mass, it'll be heavier, will be the water that it collected. Same thing here. The second chamber is my CO2 absorber, right? So what happens here is all the CO2 that comes out, it goes right through this chamber, but it gets captured here. So if I weigh this chamber beforehand and then weigh it after, that extra mass that it's accumulated will be my carbon dioxide mass. All right? So it's a very simple apparatus. Sometimes what you'll see is an initial chamber here that has copper 2 oxide, and what that does is it turns the water vapor into a liquid so it can be captured a lot easier and absorbed. All right? But a very simplistic drawing right here of the carbon hydrogen analyzer. All right? So let's do a problem that uses this information. So this problem is in your PowerPoint. This PowerPoint has been updated. It's on your D2L site. And again, I'm just going to write the steps here. Remember, the steps for formula determination. For each element, I need the mass. I need the grams. Then for each element, I've got to turn the grams into moles. And then I divide by the lowest moles. All right, and that will get me my formula. So our first question, and we'll be using this. Our first question says a sample of a hydrocarbon. So for a hydrocarbon, I know my formula is C something H something. And that's what we have to find. What are these numbers that go right in there? Was burned to produce 1.36 grams of water. So water was equal to 1.36 grams and 5.22 grams of carbon dioxide. All right, so I just wrote down the information from the question. All right. So this is what I need. This is what I'm given. I'm going to move this now because I'm going to need some space here to do this. So the question is just going to go off to the side. We'll get that done. And I'll do my answer in blue, like a blue pen. All right. So whenever I do this, I always start with the C first. So I always do the carbon first. Even though the water was given first in the question, I always do carbon first. So carbon dioxide was equal to 5.22 grams. And the water was equal to 1.36 grams. I always start with what I'm given. So there's the two things I was given. I started with those. All right? The next thing I'm going to do is I'm going to turn these into moles. All right? So I've got masses of these substances. So I'm going to turn them into moles using their molar mass. Now, here's a little bit of a change from what we did before. I know I'm looking for carbon, but the mass given is not carbon. It's carbon dioxide. So this 5.22 grams is just not carbon. It's carbon and oxygen combined. So I have to divide it by the molar mass of carbon dioxide. So 2 oxygens plus a carbon using my periodic table. So when I add 12.01 plus 16 plus 16 for the second oxygen, I get 44.01 grams per mole. All right. Water, I add 16 off the periodic table, the mass of oxygen, plus 2 times 1.01, the mass of hydrogen, and I get 18.02 grams per mole. And then I use my calculator Amatic 3000, and they end up being 119 moles and 0.075 moles. So there's my 2 molar amounts. Now again, I had masses, I changed them into moles. But my moles here are not of carbon and hydrogen. So we're used to just dividing now by our lowest mole number. So we divide by this. But we can't do that here. And the reason for this is moles of carbon dioxide. That's moles of CO2. This is moles of water. The molar mass we use is for water. The molar mass we use here is for carbon dioxide. So I can't divide by the lowest mole number yet because I need moles of carbon and moles of hydrogen to do that. And I don't have moles of carbon and hydrogen. So this is the extra step. I'm going to do the extra step involved with carbon-hydrogen analysis in pink. So I'm going to bring this stuff down here. So CO2, I've got to convert that into C. And H2O, I've got to convert that into H. All right? So CO2, converting that into C, I take my 0.119 moles of CO2. I'm going to move this down a little bit. I'm going to multiply it by every carbon dioxide has 1 CO2 or 1 carbon. Every one of these carbon dioxides has 1 carbon. So I multiply it by 1 mole of carbon for every mole of CO2. All right? If I look at the formula for carbon dioxide, there's a little 1 here we don't see. So if I have 1 carbon dioxide, I have 1 carbon. If I have 10 of these, I have 10 carbons. If I have 20 carbon dioxides, I have 20 carbons. The number's the same. For every molecule, I have 1 carbon. So if I have a mole, which is 602 hexillion carbon dioxides, I have a mole or 602 hexillion carbons because it's the same amount, right? So that number will stay the same, only now it's going to be 0.119 moles of carbon. All right? Now we'll do the oxygen. We had 0.075 moles of H2O. And we're going to multiply that by, if we look at H2O, every molecule of water has 2 hydrogens. So if I have 1 water, I have 2 hydrogens. If I have 10 water, I have 20 hydrogens. If I have 100 waters, I have 200 hydrogens. So it's 2 moles of H for every mole of H2O. And what that does is when I multiply, moles of water on top and moles of water on bottom cancel. Same thing with the moles of carbon dioxide above. They cancel. And I'm left with moles of hydrogen. And that number is going to be 0.150. All right? So this step right here is the new step, this pink part. And all I did was take my moles of carbon dioxide and convert them to moles of carbon, my moles of H2O into moles of hydrogen. And I'll put moles up here in small letters just so that you know. All right? Now that I have the moles of the elements, now I can go back into here and I divide by my lowest mole number. Because now I'm dealing with carbon and hydrogen, not carbon dioxide and water. So my lowest mole number is this one, 0.119 moles 0.119 moles. That one will be 1, and this one ends up being 1.26. We've seen this before. And what that means is that we have to multiply by something. All right? So what we have to do here is we've got to get rid of this. Now think of this as 0.25. Right? 0.25 is like 25 cents. To make that a nice round number, I have to multiply it by 4. Now I know we haven't done multiply by 4, and I forgot about that when I did. I'm cutting down what we have to do sometimes because of the pandemic situation of that. But what we would do is we'd multiply both of these by 4. And this one becomes 5, and this one would become 4. So therefore, the empirical formula is C4H5. All right? Now, I know I used 0.25. I would basically treat that like 1/4 of something. So I know we use 0.26 here or 0.25 here. I won't be doing that in any evaluations or assessments that I have that you have to do. You might get a 0.33 or a 0.5, which we dealt with earlier, but I won't do this one. But I wanted to put it out there because it does exist. All right? So this is our empirical formula here for number 1. All right? So it's basically the same. We've done this before where we've gotten an odd decimal and we've had to multiply it by 2 or 3. We've done this before and we follow these steps. It's the stuff in pink that is new, but it's actually really easy. Moles of carbon dioxide, converting it into moles of carbon. Moles of water getting converted into moles of hydrogen. All right, we're going to do the next problem on the PowerPoint in just a second. What you should do now is pause the video, get this down into your notes while I set up for the next question. So pause the video, and I'm going to erase. I almost feel like a Zamboni when I clear this off. The board comes out so nice and white. Nice and clean looking. It's like the ice. All right. So, our next question. It says a sample of an unknown hydrocarbon. So once again, we've got a hydrocarbon. And we don't know the subscripts that are there. It's burned in a carbon hydrogen analyzer and produces 3.94 grams of water and 9.62 grams of CO2. The measured molar mass of the compound is 84 grams per mole. So the molar mass is 84 grams per mole. And it wants the molecular formula. So not the empirical anymore. We want the molecular formula, the real deal. So I'll put that here, molecular. All right. Excuse me. So I'm going to move this because I need more of the space. And then we'll set this question up and we'll be off to the races, okay? So let's do that. I'll move this out of the way. We've got all the information that we need. This is what we're looking for. When we combusted it, we got this. Molar mass, a mass spectrometer could have given that to us pretty easy. And then we are looking for the molecular formula. All right? So I'm going to start at the top here with my carbon dioxide and my water. And it says I have 9.62 grams of that and 3.94 grams of this. Again, I've got my grams, I want to convert them into moles. So I'm going to divide by the molar mass of each. The beauty of this is the molar masses don't change. So once you know the molar mass of carbon dioxide from a previous question, it's still the same in the next question. Just like water is always 18.02. Carbon dioxide is 44.01. All right. So I'm going to do that. I'm going to erase this because I know that information. I'll put down here, molar mass was 84 grams per mole, and we're looking for molecular. All right. So when we do that, we end up with grams divided by grams is no grams. We'll be left with moles. And both of them end up as 2.19 moles. This is moles, though, of CO2. This is moles of water. And what we need for the formula is moles of carbon and moles of hydrogen, right? So we need moles of carbon, moles of hydrogen, not moles of these things. So now we're going to do that extra step, which again I will do in pink. I'm going to take these down, and we're going to go moles of CO2 into moles of carbon. And to do that, I take my 0.219 moles of CO2 and I multiply it by 1 mole of carbon for every mole of CO2. The moles of CO2 will cancel out, and I end up with the same number because it's multiplied by 1. But now it's moles of carbon, right? The next thing we're going to do is take this, and we're going to go moles of H2O into just moles of H. So I start with that 0.219 moles of H2O, and I'm going to multiply it by 2 hydrogens, so 2 moles of hydrogen for every water. Every water has 2 H's in it, so I'm going to double it up. And when I do that, it's going to end up being 0.438 moles of hydrogen. Now I have carbon and hydrogen. Now I have my 2 elements. I go back and I divide by the lowest mole number. So my lowest mole number is the 0.219 divided by 0.219 moles. Moles divided by moles will be no moles. This one will be 1, nice and easy, and this one's going to be 2. No decimals or anything here. So therefore, my empirical is C1H2. Now, the question did not ask me for my empirical, but I need my empirical to get my molecular. All right? So, I'm running out of space. I only have down to here, and then we run out of space. So, what I want you to do is get this down, pause the video, get this down, and then I'm going to continue and do the last step, which you know, we've done this last step before. Once I show you, go like, oh yeah, okay, I know that. But I'm going to start it from here. All right? So magically, I'm going to move this up to here, and we'll have more space. But I need you to pause the video now and get this down. All right? So pause the video. I'm going to erase. So my empirical formula, penmanship is terrible this morning. My empirical formula is CH2. I want the molecular. This is lowest terms. Remember, empirical means lowest terms. I want the real deal. When I run in this thing, you know, in the subway or down at the baseball game or out on the street, what does it really look like? This is lowest terms. It's not what it really looks like. So what I'm going to do is I'm going to take my molar mass and I'm going to divide it by my empirical formula mass. Now the molar mass was given. It's right here. It's the 84. It was given in the original question. And the empirical formula mass I get from the CH2. So C is equal to 12.01 on my periodic table. And I've got two H's in that formula, two H's. So that's 2 times 1.01 from the periodic table. That's going to be 14, when I add these things both together, 14.03 grams per mole. So I put that up here, 14.03 grams per mole. That 3 I made small, it should be up here. There we go. All right, and when I take 84 and I divide it by 14.03, I get 5.99, so 6. So this tells me these grams per mole cancel. This tells you that the real deal is 6 times larger than that. So 6 times CH2 is equal to C6 H12. And that is my molecular formula, the real deal. All right? And that's it. That's all it's to that one. So we've done this before, and we've done a lot of the other elements of this type of problem solving before. The only thing we have to remember, right? Remember, is the stuff that I did in pink today. And that was where we went from moles of CO2 into moles of carbon, and taking moles of H2O and converting that into moles of hydrogen. All right? And the carbon-hydrogen analysis, it's the only set of problems that we do this in. All right? Anyway, that's all I got. If you look at the next slide on our show, of course, there's Beaker and Professor Bunsen Honeydew and their own homemade carbon-hydrogen analyzer. Probably going to lead to an explosion or a fire if I know those two. Anyway, if there's any questions, comments, or concerns, you can voice them in the comments section below this video, or you can reach out to me if you're one of my students through Edsby. I'll get back to you right away. There's a sheet on the D2L site that deals with decomposition of hydrated salts, decomposition of oxides, decomposition of hydrocarbons, and formula determination from the products of those decompositions. Work on that. If there's any questions, please reach out to me. Don't sit there and not know. You gotta ask. Ask, ask, ask away. Anyway, that's all I got. So hopefully you understood everything today, and I'll see you soon. Bye-bye.